Welcome to another deep dive. Today, we're exploring something super interesting,
Okay.
using physics to understand
Physics.
how we learn new skills.
Huh.
You might think that's a weird combo.
Yeah.
But the research we're looking at today
Okay.
uses physics-inspired models to
That's smart.
uncover some surprising things about skill development,
Okay.
even in artificial neural networks.
Mm-hmm.
So get this.
Okay.
One of the things they found is this thing called the domino effect.
The domino effect.
Have you ever noticed how sometimes learning one skill
Mm-hmm.
seems to unlock your ability to learn another,
Yeah.
even if they seem completely unrelated?
That's exactly what the domino effect is all about.
Really?
The researchers saw this happening in neural networks, which are basically computer systems
Right.
designed to mimic how our brains learn.
Okay, so walk me through this.
Yeah, sure.
What kind of experiment did they do?
They were training a neural network on two tasks, which you can think of as two distinct skills.
Got it.
But here's the catch.
Okay.
One task was presented to the network way more often than the other.
Oh, interesting.
Like 10 times more.
So logically, you'd think the network would just learn the more frequent skill 10 times faster.
Right.
Right.
You'd think so.
Yeah.
But that's not what happened.
Oh, really?
The less frequent skill only started to improve rapidly after the more frequent one was mastered.
Wow.
It was like the network needed to unlock that first skill to even begin understanding the second one.
That's wild.
Yeah.
It's like those old video games where you couldn't access certain levels until you'd beaten the previous ones.
Yeah.
Almost as if the skills were literally lined up like dominoes,
Right.
waiting to be knocked over in a specific order.
That's a great analogy.
I try.
And what's even more interesting
Yeah.
is that this domino effect seems to be particularly pronounced
Okay.
when using specific optimization algorithms, like one called SignGD.
Sign-G.
Optimization algorithms are basically the mathematical instructions
Okay.
that guide how a network learns.
So certain algorithms are better at triggering this domino effect than others.
Exactly.
That's fascinating.
Yeah.
It makes me wonder what's going on under the hood
Yeah.
that causes this.
That's exactly what the researchers wanted to figure out.
Oh, okay.
They wanted to understand the why behind this sequential learning phenomenon.
Right.
And to do that,
Right.
they took a cue from a classic physics tactic.
Oh.
Simplification.
Simplification. Like
Yeah.
how physicists will use the analogy of a spherical cow to make complex calculations easier.
Precisely.
Wow.
Physicists often strip away unnecessary details
Right.
to get at the core principles governing a system.
Yeah.
And that's what they did here with skill learning.
Okay.
They developed 3 models,
Okay.
each with a different level of simplification.
Interesting.
They called them the geometry model,
Okay.
the resource model,
Okay.
and the domino model.
Got it. Okay, so let's break those down.
Sure.
What's the geometry model all about?
In the geometry model,
Okay.
each skill is represented as a direction
Uh-huh.
or vector in a high-dimensional space. Imagine each skill having its own unique arrow.
Okay.
And learning involves moving along these arrows
Yeah.
in a vast landscape of possibilities.
So the network is navigating through this space,
Right.
trying to figure out the right direction for each skill.
Exactly.
That makes sense.
The geometry model is kind of like a map
Got
of the learning process,
it.
showing how the network adjusts its internal parameters to acquire different skills.
That's a cool visual.
Yeah.
So what about the resource model?
Yeah.
How does that simplify things?
The resource model gets even more to the point.
Okay.
It says, look, the network has a limited set of parameters,
Right.
which are like its building blocks for learning.
Okay.
And these parameters are treated as resources that different skills have to compete for.
So it's like a bunch of kids fighting over the same set of Legos.
Yes.
Some skills are hogging all the pieces.
That's a perfect way to put it.
Awesome.
The skills with stronger gradients, which basically means they require the network to change more to be learned,
Right.
get a bigger chunk of the resources.
Uh-huh.
Yeah.
So that explains the domino effect.
Exactly.
If one skill is super common
Right.
and demanding a lot of resources,
Yeah.
the less frequent skill is left with scraps until the dominant one is fully learned.
That's exactly the insight the resource model provides.
Wow.
It highlights how the allocation of these limited resources can create a bottleneck, forcing skills to be learned in a specific order.
And the domino model takes us even further, right?
Absolutely. The domino model is the most extreme simplification.
Okay.
It just assumes skills are learned in a strict sequential order,
Uh-huh.
one after the other, like dominoes falling in a line.
Wow.
No competition,
Yeah.
no fancy resource allocation. Just a straight path from one skill to the next.
So even with this extreme simplification,
Yeah.
they were still able to learn something about how these networks learn.
Believe it or not.
Really?
All three of these models,
Yeah.
despite their varying levels of complexity,
Yeah.
can make surprisingly accurate predictions about how real neural networks learn.
Wow, that's amazing.
It really highlights the power of using simplified models
Yeah.
to uncover those fundamental principles.
So by stripping away all the complexity,
Exactly.
they're able to reveal these elegant,
Yeah.
almost physics-like laws governing skill learning.
Yeah.
But it gets even cooler.
It does.
Right.
What?
They didn't stop there.
What else did they do?
They went on to apply these models to some of the biggest mysteries in machine learning.
Oh, cool.
What kind of mysteries?
Well, one of those mysteries is something called neural scaling laws.
Neural scaling laws.
Are you familiar with those?
I've heard the term.
But I'm not entirely sure what it means.
Well, neural scaling laws describe this incredible observation that the performance of AI models improves predictably as we increase things.
Okay.
Like the amount of data they're trained on,
Right.
the size of the model itself,
Good.
and the amount of computing power we throw at them.
Makes sense.
It's one of the reasons we've seen such incredible progress in AI in recent years.
Yeah, I've heard of that.
So bigger models,
Yeah.
more data, more computing power equals better performance.
Right.
That seems pretty intuitive.
It does, but what's fascinating is that this relationship is surprisingly predictable.
Oh.
And our physics-inspired models actually offer some clues as to why this might be the case.
Okay.
For example, the resource model suggests that limited resources are the very reason scaling is necessary.
So we need bigger models and more data.
Right.
Because we need more resources to learn more complex skills.
Exactly. It's like if you want to build a bigger house, you need more building materials.
Yeah.
The resource model gives us a way to think about scaling in terms of this fundamental constraint.
That's a really cool way to think about it.
Yeah.
So are they saying these models could actually help us improve how we train AI models?
Potentially, yes.
Like, could they lead to more efficient training methods?
That's definitely the hope.
Yeah.
These models could help us understand and maybe even optimize neural scaling laws.
Okay.
By taking into account how often a skill appears during training, how those limited resources are allocated, and even how different optimization algorithms behave.
Interesting.
In fact,
Yeah.
they even found that the geometry model
Okay.
produced a scaling exponent
Okay.
that was incredibly close to what was observed in the famous chinchilla language model.
The chinchilla model.
Yeah.
Oh, I've heard of that.
Chinchilla was a breakthrough in language modeling because it demonstrated that you could achieve better performance by training a smaller model on a much larger data set.
Whoa, so we're talking about real-world applications here.
Yes.
This isn't just theoretical musing.
Right.
This could change how we design and train the AI of the future.
It's still early days,
Okay.
but the possibilities are incredibly exciting.
Yeah.
And there's even more to uncover.
Wait,
Yeah.
there's more.
Yeah.
What else can these physics-inspired models help us understand?
Well, one thing they shed light on
Okay.
is a phenomenon called grokking,
Grokking.
which is this fascinating behavior where a model seems to suddenly get it
Okay.
after a long period of just memorizing the training data.
I've heard about grokking.
Oh, yeah.
It's like when a student is cramming for a test
Yeah.
and suddenly all the concepts click into place.
Right.
It's this sudden shift
Yeah.
from rote memorization to true understanding.
You nailed it.
I knew it.
And what's interesting is that the model suggests that using different optimization algorithms. Okay.
Like our friend SignGD
Yeah.
can actually reduce or even eliminate grokking.
So instead of slogging through that memorization phase,
Right.
the model can start understanding and applying concepts much faster.
Precisely.
Wow, that's interesting.
And that has huge practical implications.
Okay.
Using the right optimization algorithm can save tons of time and resources when training models.
Right.
It's like finding a shortcut through all that tedious cramming.
Amazing.
Yeah.
So these models are like a secret weapon
Kind of.
for making AI training more efficient.
Yeah.
I can't wait to see what other optimization tricks they've uncovered.
Oh, yeah, there's a bunch.
This is getting me really excited about the potential here.
You and me both.
Yeah.
Like, there's so much to explore.
Awesome.
In fact, one of the things they looked into
Okay.
is a technique called data reweighting.
Data reweighting.
And this one is all about making sure the less frequent skills.
Okay.
Those that get overshadowed by the more dominant ones.
Still get the attention they deserve during training.
So like,
think back to that resource allocation analogy.
Okay.
We want to make sure the Legos are being distributed a bit more fairly.
Yeah.
So those less common skills don't get completely left behind.
That makes sense.
Yeah.
But how do you actually do that?
Right.
How can you tell a neural network,
Right.
hey, pay more attention to this rare skill over here?
So good question.
It's not like you can just point to a specific part of the data
Yeah.
and say, this is important, focus on this.
You're right. It's not that straightforward.
Okay.
You can't just neatly label everything in a complex data set.
Right.
Especially with something like language modeling.
Yeah.
Where you have this massive stream of words.
Right.
Without clear boundaries between skills.
Yeah, that's tough.
It's more like trying to figure out the subtle patterns
Uh-huh.
within a giant tapestry.
Okay.
Rather than sorting objects into neat little boxes.
And if you can't directly control what the network focuses on, how does data reweighting work?
Well, remember how we talked about those less frequent skills
Yeah.
often lagging behind during training because
Got it.
of that resource bottleneck?
Yes.
That lag actually gives us a clue.
Okay.
Because they're being learned more slowly.
Mm-hmm.
Those less frequent skills tend to have higher losses during training.
Losses.
Yeah.
Remind me what that means again.
Basically, the loss is a measure of how far off the network's predictions are
Okay.
from the actual correct answers.
Right.
So if the network is struggling to learn a particular skill,
Yeah.
its predictions for that skill will be less accurate,
Okay.
resulting in a higher loss.
So they're using those higher losses as a signal that a skill needs more attention.
Exactly.
Right.
That's clever. Higher loss equals lower frequency. So they can use the loss values to identify those rare skills that are being neglected,
Oh.
and then they reweight the data
Okay.
so that examples related to those high loss skills get more emphasis during training.
It's like giving the network a little nudge.
Yeah.
Saying, hey, spend some extra time on these. They're important.
Right.
Even though you might not see them as often.
That's a great way to think about it.
Cool.
And they actually tested this out with a GPT-2 model.
GPT-2.
Which is a type of large language model.
Okay.
And trained it on a massive text data set.
Wow.
And you know what?
What?
By focusing on those hard examples,
Uh-huh.
the ones with higher losses,
Okay.
in the early stages of training,
Yeah.
they actually sped up the learning process.
Wow, that's amazing.
It is pretty cool.
So this simple idea,
yeah.
inspired by those physics models,
Right.
actually led to a real improvement in how fast a language model could learn.
Yeah.
But I'm guessing it's not quite that simple, right?
You're right to be skeptical.
Okay.
They did find that if they kept reweighting the data for too long,
Oh, really?
it could actually backfire
Huh.
and slow things down in the long run.
Why would that happen?
Well, it turns out
Right.
that in any real-world data set,
Right.
you're going to have some noisy data.
Noisy data.
These are examples that are just inherently messy
Yeah.
or don't really fit the patterns the network is trying to learn.
Ah, I see.
Yeah.
So those noisy examples are always going to have high losses,
Right.
even if the network is doing a good job overall.
Exactly.
Okay.
And if you keep telling the network to focus on those high-loss examples, it can get stuck trying to make sense of the noise
Yeah.
instead of focusing on the true underlying patterns.
That makes sense.
It's like trying to learn a language from a textbook full of typos.
Right.
It's going to throw you off course.
So it's a balancing act.
Yeah, you could say that.
Boost those low-frequency skills early on
Right.
to give them a fighting chance,
Uh-huh.
but then ease off
Yeah.
as the model starts to generalize and learn those deeper patterns.
That's the key.
Okay.
Finding that sweet spot is crucial for optimizing the learning process.
Right.
It's like being a coach.
Yep.
You want to push your athletes to improve,
Uh-huh.
but you don't want to overwork them to the point of injury.
I love that analogy.
Thanks.
This whole conversation is really giving me a new appreciation for how intricate and subtle this whole learning process is.
Yeah.
Whether talking about AI or humans.
It really is a delicate dance.
It is.
And what's fascinating is that this data reweighting strategy
Uh-huh.
not only improves performance,
Okay.
but also raises some interesting questions about how we can actually understand
Okay.
the structure of skills themselves.
Oh, interesting.
If we can map those high-loss examples to low-frequency skills,
Yeah.
could we do the reverse?
Ooh, I like where this is going.
Could we use the way a network learns to infer what skills it's acquiring and how those skills relate to each other?
That would be amazing.
It would.
It'd be like reverse engineering the learning process itself.
Right.
Uncovering those hidden connections and dependencies between skills.
Yeah.
It makes me think about those skill trees you see in video games,
Uh-huh.
where mastering one ability unlocks a whole new branch of possibilities.
Yeah.
Could we create something like that for human learning?
That's the dream.
Yeah.
Imagine if we could analyze someone's learning journey and create a personalized map of their skills, revealing those hidden connections and dependencies.
It would be incredible.
It would,
like a roadmap for personal growth.
Yeah.
Showing you the most efficient path to mastery.
Exactly.
But are we even close to something like that?
Not quite there yet.
Okay.
But it's a tantalizing goal.
Yeah.
And these models,
Right.
with their focus on resource allocation and the interplay of skills, give us a framework for thinking about it.
I see.
But let's shift gears a bit.
Okay.
This whole idea of optimizing the learning process,
Yeah.
whether through data reweighting or choosing the right algorithm,
Right.
brings us to another crucial element.
Okay.
The optimizers themselves.
Right. The optimized.
Yeah.
Those are the algorithms that guide how a network learns.
Yeah.
Like the coaches in your analogy.
Right.
And I know there's a ton of research going on trying to find better optimizers.
Absolutely.
Especially for those massive language models that are all the rage these days.
For sure.
But how do these simplified models we've been talking about help with designing better optimizers? What's the connection there?
Well, they provide a kind of testing ground.
Okay.
A way to experiment with new optimizer designs.
Yeah.
Without having to immediately jump to those resource-intensive, large-scale models.
Okay, because that's expensive.
Exactly.
And time-consuming.
You see, the problem with evaluating new optimizers is that it's often a balancing act between simplicity and realism.
Okay.
On one hand, you can test them on simple, well-understood problems.
Okay.
But those don't really reflect the complexities of real-world training.
Yeah, it's like trying out a race car on a go-kart track. You're not really going to get a sense of its true potential.
Right.
Okay.
But then the alternative is testing them on those massive language models.
Right.
Which, as we said, is super expensive and time-consuming.
Yeah.
You don't want to waste all that time and energy on an optimizer that might not work well.
Yeah, totally.
So these simplified models offer a middle ground, a sweet spot.
Got it.
They capture some of those key aspects of large-scale training, like the high dimensionality of the data and the effects of batch size.
Yeah.
But they're still simple enough that you can run experiments quickly and get insights without breaking the bank.
So it's like a simulator for optimizers.
That's a great way to put it.
You can try out all sorts of new ideas and see what works best before you unleash them on the big leagues.
Right. And the researchers actually used their geometry model.
Okay.
That one where skills are like vectors in space.
Right.
To analyze two recently proposed optimizers called Edema, Mix, and Lion.
Interesting.
And what they found was that their simplified model could actually reproduce some of the quirks and behaviors that these optimizers showed in real-world training.
No way.
Yeah.
So they could predict how well a new optimizer would work just by running it through this simplified model.
It's pretty amazing.
Wow.
It means you could potentially weed out less promising optimizers early on, or even get hints about how to fine-tune their parameters for optimal performance. It's like having a crystal ball for optimizer design.
Okay, I am officially blown away by the power of these models.
Yeah, they're pretty cool.
They're explaining the domino effect. They're shedding light on neural scaling laws.
Right.
They're helping us design better optimizers. Is there anything they can't do?
Well...
But I have to ask, is all this focus on neural networks really relevant to us humans?
That's a great question.
I mean, our brains aren't exactly running the same algorithms, are they?
That's a great question, and one that researchers are definitely thinking about.
Okay.
While there are obvious differences between artificial neural networks and the human brain, there are also some intriguing parallels.
Okay.
We both learn.
Right.
We both adapt. We both develop skills.
Yeah.
And it seems like some of the underlying principles might be shared across these very different systems.
Right. At the end of the day, we're both dealing with information, making sense of patterns, and trying to figure out how to navigate the world.
Exactly.
It's a tough world out there.
And one of the key insights from these models that might be particularly relevant to human learning is the importance of modularity.
Modularity.
Remember how we talked about how breaking a network into specialized modules, like different departments in a company, can speed up learning? Well, there's evidence that our brains might do something similar.
So different parts of our brains are specialized for different skills.
That's the idea.
Like maybe there's a module for language,
right?
A module for visual processing, a module for motor skills.
Exactly.
And
it makes sense from an evolutionary perspective.
right.
If our brains were just one big tangled mess, learning new skills would be incredibly inefficient.
Right.
But if we have specialized modules that can develop somewhat independently, it becomes much faster and more flexible.
That's interesting.
It's like having a team of experts working in parallel.
Right.
Rather than one person trying to do everything at once.
That's fascinating.
Yeah.
So studying these artificial systems might actually be giving us clues about how our own brains are organized.
Right.
And how we can optimize our own learning.
Yeah.
I'm sensing a mind-blown moment coming on.
It's a two-way street.
It is.
By understanding how artificial systems learn, we might gain insights into the principles of learning itself.
Right.
Whether it's happening in a silicon chip or a biological brain.
Cool.
But there's one more fascinating concept these models shed light on that I think will really resonate with you, especially when it comes to human learning.
All right, you ready?
And that's the idea of task compositionality.
Task compositionality.
Yes.
Okay, now you've really got me intrigued.
Right.
Break it down for me.
We've been talking about skills.
Yeah.
As if they're these isolated things.
Right.
But in reality, most skills are built on a foundation of simpler ones.
Right. Like learning to write a novel depends on first mastering basic grammar and vocabulary.
Exactly.
Or learning to play a complex piece of music requires first learning scales and chords.
Yeah.
Like building a house.
Right.
You need a strong foundation before you can add the walls and the roof.
Exactly.
Makes sense.
And what's cool is that the resource model, that one where we think about skills competing for limited resources, can actually be extended to simulate skill learning with these kinds of dependencies.
So you can actually model how mastering one skill unlocks the ability to learn another.
Exactly.
Like you could simulate how learning those basic musical scales makes it easier to then learn more complex chords and melodies.
Precisely.
Wow.
And they did an experiment to test this out. They had a network learn to calculate 3 different XOR functions.
XOR functions.
Which are a type of logical operation.
Right.
Don't worry if you don't remember those from your computer science days.
I barely remember those days.
The important thing is that the third XOR function actually depended on the results of the first 2.
So it was like a hierarchy of skills.
Exactly.
You had to master those first 2 XOR functions before you could even begin to understand the third one.
Exactly.
That's interesting.
And what they found was that their model accurately captured the delayed learning of that dependent skill. It couldn't master that third XOR function until it had a good grasp of the first 2.
That's so cool.
It is.
It's like they're simulating those aha moments where you suddenly see how different concepts fit together and build on each other.
I think.
And this brings us back to that reverse problem we talked about earlier, right? Can we use these models to work backward and figure out the hidden dependencies between skills and humans?
That is the ultimate goal.
Like, could we analyze someone's learning trajectory and create a map of their skills and how they relate to each other?
That's the dream. Imagine if we could analyze someone's learning journey and create a personalized map of their skills, revealing those hidden connections and dependencies.
Yeah, like what leads to what?
Think about how powerful that would be for education.
Oh, yeah, totally.
For training, even career planning.
It would be revolutionary. Almost like having a personalized GPS for skill development.
Exactly.
Showing you the most efficient route to mastery.
Yeah.
But you said we're not quite there yet.
Right. Yeah. Not yet.
Okay.
But it's a goal worth striving for.
Yeah.
And these models we've been discussing, with their focus on resource allocation and skill interactions, provide a framework for approaching this challenge.
That makes sense.
They're not just theoretical curiosities.
Yeah.
They're tools for understanding and ultimately improving how we learn, both individually and as a society.
I like that.
Yeah.
This whole conversation has been incredibly eye-opening.
Good. Glad to hear it.
We started with this wild idea of applying physics to skill learning.
Yeah, sounds crazy.
And we learned about the domino effect, where mastering one skill seems to unlock the ability to learn others, even if they seem completely unrelated.
Totally.
Then you explained how researchers developed those simplified models, the geometry model, the resource model, and the domino model, to explain why this happens.
Exactly.
And those models turned out to be far more powerful than anyone expected.
Yeah, they were surprisingly effective.
They're not just explaining the domino effect.
Yeah.
They're giving us insights into neural scaling laws, optimization strategies, the benefits of modularity in neural networks, and even potential clues about how the human brain is organized.
It's pretty amazing what they can do.
It is mind-boggling to think about how these simple models, inspired by physics, are revealing such profound insights about learning.
I know, it's pretty cool.
But here's the question that's been swirling in my head this whole time.
Oh, yeah.
We've talked about applying these models to neural networks.
Right.
And even hinted at connections to human learning.
Yeah.
Could we take it a step further?
What do you mean?
Well, if we can map the skills of a neural network onto this resource framework, could we do the same for human skills?
That's interesting.
Could we analyze how people learn?
Oh, okay.
Identify those key dependencies between skills?
Yeah.
And then actually optimize our own learning processes?
Hmm.
It's a bold idea, but would it be possible to create a signed GD for humans?
That's a truly fascinating question, and one that pushes the boundaries of what we currently understand.
Yeah, I know it's kind of out there.
It's uncharted territory, but not entirely implausible.
Okay.
If we could identify those fundamental resources that underpin human learning, things like attention,
Right.
memory, motivation, and perhaps even factors we haven't discovered yet, could we develop techniques to allocate those resources more efficiently?
That'd be amazing.
Could we design learning environments or training programs that minimize interference between skills and maximize those aha moments of connection?
It's like the ultimate life hack, unlocking our full learning potential by understanding the hidden physics of skill development.
It would be pretty amazing.
Imagine being able to learn any skill more efficiently.
Right.
And even discover hidden talents you never knew you had.
It's a bold vision, but the research we've explored today suggests that it might not be as far-fetched as it seems.
I like that.
It's a challenge I'm incredibly excited to see tackled in the years to come.
Me too.
Yeah.
This deep dive has been a wild ride, and it's left me feeling incredibly optimistic about the future of learning.
Me too.
Who knew that physics could hold the key to unlocking our full potential?
It's pretty amazing.
So to all you listeners out there, I encourage you to reflect on your own learning journeys. What are those skills you've always wanted to master? What are those hidden connections waiting to be discovered? Maybe, just maybe, the insights from this research can help you find those shortcuts to mastery. Until next time, keep those brains buzzing and never stop exploring the fascinating world of learning.